So we had started section 3.3 last time. It's called the theory of equations. And we had taken a look at this idea of how powers, exponents, namely on factors, related to the multiplicity of roots. So if we had, say, like on this one, where there's a power of 2 that's circled here, it means that that 0 has a multiplicity of 2. It occurs twice. Same thing over here when we had this one. We had that power of 3 on x cubed. So that 0, which was x equals 0, had a multiplicity of 3. We're going to use this a lot more in section 3.4 as we move forward. So all of my powers are actually the multiplicity, how many times the roots actually exist. And that relates, one of the things it relates to anyway that we didn't get to is part of this graphing facts. So we'll pick up here from last time. So some ideas about graphing that we will use in section 3.4 and come back across. So when you have multiplicities considered, a polynomial of degree n has n roots. So you might have heard me sort of making those comments as we were doing homework questions. Look, it's a power of 3, I got 3 solutions. Look, it's a power of 4, we got 4 solutions. That's true as long as you consider multiplicities. So if it's repeating, that doesn't mean that you have 4 distinctly different roots. There might be some where they overlap one another, right? Where it becomes x equals 2 twice. So there are 4 roots if it's a power of 4, but some might be duplicates. When you have complex roots, they come in conjugate pairs. So if you'll remember conjugate pairs, it means that if you have I, actually let me give you a different one, 5 plus I, you also have 5 minus I. Okay? So whatever you have one, you have the other one automatically, anytime you have complex roots of real polynomials. Let me also mention if you had, say, negative 3i, so there's not a constant part that's just a whole number, then there's also a positive 3i. Okay, so that's the conjugate pair. So the conjugate pair of negative 3i is positive 3i. This is what I was mentioning a moment ago about the multiplicities being important in the graphing. If your multiplicity is odd, the graph will cross through the x-axis. Okay, so it will completely cut through the x-axis. So you have an image where it looks like this. It actually cut through. Hang on. Right here. Okay, that's the crossing through the x-axis. Forgot my lights. If your power is even, it doesn't cross through the x-axis. It bounces off of it. So it ends up looking kind of like our typical or traditional parabola equation. So we have something that looks like this bouncing off. Then this right here would have had a multiplicity of 2, 4, 6, something even in order to make that happen. And we'll come back more to those ideas in section 3.4, but that is the relationship and why multiplicities matter. So you might be thinking, well, what difference does it make? Well, we'll do a graph in terms of those ideas in 3.4. So what we're going to do on the next problem is we're going to kind of do the problem that we did last time in reverse. So over here, what you'll notice is that we were given an equation on both of these examples, and we did some kind of factoring in order to set things equal to 0 and solve, right? That was the idea. And at the very end, we get a list of zeros. X equals this, X equals this, X equals this. We're basically going to be working on these last few problems from the bottom up. We're going to be given that x equals this, 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 and this, and we're going to be backtracking up this sort of problems that you see here to find an equation that satisfies those conditions. Okay? So over here, we're told that these are our given roots, or zeros. So that means x is equal to 2, x is equal to 4, and x is equal to negative 3. That's what we're told. So what I want to do is I want to sort of work my way back up this solution. So you'll notice that the reason we got x equals, say, 3 right here was because we had an equation set equal to 0, right? So we're going to take all 3 of these equations and we're going to get them all to say equals 0. So we're going to move the negative 2, or the 2, back on the side with the x. So it says x minus 2 equals 0. And we're going to move the 4 back on the side with the x, so it says x minus 4 equals 0. And we're going to move the 3 back on the side with the x, so it says x plus 3 equals 0. What that means then, again, working our way backwards, is that each one of these, if you compare from here, came from a factor set in parentheses, multiply together. So now we're going to do that. We're going to take each of these, put them in parentheses, multiplied together. Now each one is individually equal to 0, so when you multiply different factors that are equal to 0 together, they still will equal 0, right? 0 times 0 times 0 is still 0. So this is all equal to 0. And the last thing that we have to do is to undo the factoring, which means we multiply it all back out. So we multiplied polynomials together back in Chapter P, way back in January and February, right? We're going to do that here. Now, practically speaking, or I shouldn't even say practically, but realistically speaking, you can multiply these out in any order you'd like. Practically speaking, there's sometimes a nicer order than others. On this one, it doesn't matter. Okay, so we're just going to multiply from left to right. So we're going to multiply these two together first, clean it up, simplify it as best we can, and then we'll multiply it by the next term, or the next factor. So we multiply first times first, so we have x times x, so that's x squared. We have our inner terms and our outer terms. So I have, in whichever order you wish, negative 2x and negative 4x. And we have our last terms, which is a positive 8. And then I have an x plus 3. So those two can be combined. We definitely want to consolidate and combine pieces before we start expanding and multiplying more things out. So we will get x squared minus 6x plus 8. Now, if you can go straight from here to here, you can do the combination of those 2x and the 4x as you go without writing them out. That's fine. You can do that. I don't have a problem with that. And then we have this times x plus 3. All right, so now I need to multiply a trinomial, 3 terms, times the binomial, 2 terms. And there's more than one way you could do this. I tend to do it in the same order every time so that I don't forget any pieces. So what I always do is I always take the first term, in this case it's x squared, and I multiply it by everything in the binomial. Okay, so that's how I'm going to approach it. I'm going to take x squared times x is x cubed. X squared times 3 is 3x squared. And then I'm going to take the negative 6x and do the same thing. Negative 6x times x is negative 6x squared. And negative 6x times 3 is negative 18x. And then I'm going to take my last term, the 8. 8 times x is positive 8x. And 8 times 3 is 24. Okay, is everybody doing okay so far? Okay. The only thing we have left to do is to combine like terms. So you'll notice that these two both are x squared, and these two are both x. So they will be able to be combined. I do have an x cubed at the beginning. I have positive 3x squared and negative 6x squared, which gives me, that's right, negative 3x squared. Then I have negative 18x and positive 8x to give me negative 10x. And my last one was positive 24. So what are some things you could do besides just backtracking through this to check to make sure you did it right? Well, you could plug the equation, the original 3 zeros you have, into it and see if I plug them in, do I get 0? You could look at a graph and you could see whether or not the graph appears to cross at x equals 2, x equals 4, and x equals -3. Those are different sort of check steps you could do just to make sure you didn't have any multiplication errors as you multiplied that back out. Okay, so this one had all real solutions that we were given to start with, all real numbers, and nice ones at that, actually. They were whole numbers, or at least integers. They weren't fractions, in other words. Part B expands this idea a little bit to say, okay, well, what if they weren't real numbers? What if they're imaginary numbers? So first of all, it's important to notice that this actually, as it's given on Part B, satisfies this part where it says complex numbers, common complex pairs, or conjugate pairs, right? So if I have the -9i, I have to positive 9i. So they're there. The conjugate pair is there. So as I'm working with this, I work with it the same way. This is saying x equals -9i, and this is x equals positive 9i. And we're going to move it, right? So we're going to add our 9i. So x plus 9i is equal to 0. And we're going to subtract our 9i. And so x minus 9i is equal to 0. These then will become my factors. So I have x plus 9i, and I have x minus 9i. Now, if, after you've done a few, or maybe even right now, you can jump from here to here because you see the relationship and how it's working, you can do that. That's okay. All right, so if you don't need to see this part here in the middle for setting them equal to 0 and so forth, all that kind of stuff, I'm okay with that. This is going to equal 0 since they each individually equaled 0. And we need to multiply it back out. So we're going to take our first term, x times x, which is x squared. Our outer terms, x times -9i is -9ix. In the middle, 9i times x is positive 9ix. And then our last terms, 9i and -9i, give me -81i squared. Now, these two, what happens? Yeah, they add to 0, right? And in fact, that's kind of the whole point. They're occurring in conjugate pairs because the inner terms and the outer terms match, save for the sign, right? The signs are opposite, everything else are identical. So that's part of the process. So if you recognize that that's happening, you don't have to write that out either. So you might, as you're looking at this, simply jump to the idea that this is x squared minus 81i squared equals 0. So if you jumped to this step because you recognized that, you caught that along the way, that's great. If you don't, just multiply it out traditionally so you don't lose any of the pieces or get concerned that you might lose them. What is I squared? It is -1. So this I squared here needs to be written as -1. And when I have a negative times a negative, this ends up giving me a positive 81 at the end. So this is my polynomial function.
Wait, real quick, can you go to the first example?
Mm-hmm. Get it? Okay. You bet. Okay, any questions on this one? Okay. So I mentioned when we saw this happen that these are occurring in pairs, right? Positive 9i have a negative 9i. What you'll notice on part C is that they told you you have a negative I, but it's up to you on this one to recognize that there is a 0 at, what's the other one? I. So whether they tell you or whether they don't tell you, you should know and have to recognize and put it in that there is another 0 here that is required in order for this to create a polynomial with real coefficients. So even though they don't list it, it is a required necessary piece that has to now be included. So there are 3 zeros here. There's x equal 4, x equals negative I, and x equals I. All right, so again, if you can jump straight to the factors, that's great. If not, let me show you and remind you how you're doing this. You're subtracting the 4, so it's x minus 4 equals 0. You're adding an I, so x plus I equals 0. And you're subtracting an I, so x minus I equals 0. And those create the factors x minus 4, x plus I, and x minus I. I mentioned on this problem over here that multiplication can be done in any order. We have 3 factors to multiply out together here. You can multiply whichever 2 together you really want to. But sometimes there's a naturally easier choice. Anytime that you are dealing with something that has complex pieces in it, like this one, right? There's an x plus I and an x minus I. You absolutely should be multiplying the complex conjugate pieces together first. And the reason you should is because things consolidate and clean up, right? So you notice that when we originally started, this had 4 pieces and it consolidated down to 2, right? So we want to make sure that we do that on all problems that have conjugate pairs because they will consolidate down as well. So I have the x minus 4 is just going to hang out here for now. And we're going to distribute out the part that I highlighted in blue there at the end. So x times x is x squared. The inside and the outside terms, as mentioned before, always cancel out. If you want to write them out, I'll let you. If you don't need to write them out, I'll let you not. It doesn't matter to me. I'm going to avoid it this time just for sake of space. So the inner and the outer cancel. The last 2 terms, however, I do need them. So I have positive and negative, so that's a negative. And then I times I is I squared. So on this one then, here is x minus 4.
Wouldn't it be x squared minus 1?
Close, minus negative 1.
Oh, plus 1.
Yeah, so it'll be a plus 1. So there's a minus in there already, right? This piece comes down as negative, but I squared is negative 1. So yes, Mari, we're going to have now an x minus 4 and an x squared plus 1. Okay, so we're going to distribute this out. Foiling is fine since it's 2 by 2, right? Binomial times a binomial. X times x squared is x cubed. My outer terms x times 1 is x. My inner terms negative 4x squared. And my last terms is negative 4. You're welcome to stop there. There's absolutely nothing wrong about this. If you check the back of the book, they're going to put it in descending order of exponents. And so they're going to switch it and they're going to write it as x cubed minus 4x squared plus x minus 4, which is not any more correct than the other version. Either one's fine. Any questions on that? So remember, you have to include the conjugate pair, whether they tell you it's there or not. Okay, the last example is the most complicated. Notice how this sort of developed. We started with real numbers, right? 3 real zeros. We were given a problem that had a conjugate pair given. Then I gave you one that was missing the conjugate pair that we have to remind ourselves to include. But again, it has 3 terms. And then this last one is harder, and the reason it's harder is because it says x plus I. I didn't say that right. 7 plus I. It's not just I, or 9i, or 3i. It's got addition in the complex piece you're given.
So we just do the opposite. Would we have to add the opposite?
Yep, what would the opposite one be, Amari?
Would it just be 7 minus that?
It would. So I have 3 of these, just like I had 3 before. Now, while I told you before that if you can jump straight from the negative 9i and 9i over into the x plus 9i and x minus 9i, and that's cool, it's a little harder to do here. Let me show you why. So I'm going to write this one out. This is x equals 7 plus I, x equals, and I'm going to put the 7 minus I just next to it because eventually I want to multiply them together anyway. And then I have x equal 3. The reason that this one's harder is because not only do I have to move the 7, I also have to move the I. So both of the signs change as I do this. I have x minus 7 minus I equals 0. Over here, I have minus 7 and plus I. So I have x minus 7 plus I equals 0. And then on the last one, when I subtract my 3, I have x minus 3 equals 0. So it's a little more complicated to get the signs correct when you have a conjugate pair that has a real component added or subtracted with an imaginary component. So it's a little bit easier to keep them all straight if you actually write this one out anyway. So I have x minus 7 minus I, x minus 7 plus I, and x minus 3. This is messy. The reason it's messy is because there are 3 terms here and 3 terms here. And when you multiply 3 terms times 3 terms, you get 9 terms. I'm going to get 9 different pieces when I multiply this all out. The good news is, because I'm dealing with conjugate pieces, they are going to consolidate and sort of squish down into something smaller. I'm not going to end up with 9 pieces when I'm done. Okay? So we're going to multiply these out by taking them piecewise. So I'm going to take the first one, x, and I'm going to multiply it clear through this one. So x times x is x squared. X times negative 7 is negative 7x. And x times I is xi, or ix. It doesn't matter what order you put them in. We'll do the next one. It's the negative 7 that gets distributed through. So negative 7 times x is negative 7x. Negative 7 times negative 7 is positive 49. And negative 7 times I is negative 7i. And then we have the negative I at the end to distribute through. So negative I times x is negative ix, or xi. Negative I times negative 7 would be positive 7i. And then negative I times positive I would be negative I squared. All of that, those are my 9 terms, eventually, after I consolidate, will be multiplied by x minus 3. It's messy, but it's about to clean up. So you should notice some pieces that eliminate each other immediately. What do you notice that eliminates each other? Fantastic. There's a negative 7i and a positive 7i. I'm down to 7 terms instead of 9. What else? Yeah, there's a negative ix and a positive ix. Now I'm down to 5 terms already. I'm almost half the terms. It's great. There's a couple that combine still, right? These two combine. They don't eliminate each other, but they do combine. So that's helpful. So let's see what we have. I have x squared. I have a negative 14x. I have a 49. And then I have this piece at the end, which is minus I squared, which means I have minus a negative 1. So what is minus negative 1? Positive. So I have positive 1 added to my 49. So I really have x squared minus 14x plus 50. So those 9 terms became 3 terms after we consolidated things, canceled things, and so forth. Okay? Now, while this is the easiest, if you did decide that you were going to multiply one of these conjugate pieces through the x minus 3, you could do that. You're just going to have a far messier problem. So if you thought this was already messy, I promise you it will be worse if you try to do it differently. So this is definitely our best option for cleaning things up quickly. I do still need to multiply out this last piece. So let me make the screen a little bit smaller on the work. Hang on. And we'll distribute this out. So I've got my x squared, and it's going to go through the x minus 3. So x squared times x is x cubed. X squared times negative 3 is negative 3x squared. Then we're going to distribute our, that's not the right color. There we go. Our negative 14x through that. So negative 14x times x is negative 14x squared. Negative 14x times negative 3 is actually a positive 42x. And then the last one, which is a negative 50, positive 50, is 50 times x, so 50x, and 50 times negative 3 for negative 150. Combining like terms, these will combine, and these will combine. So I have x cubed. I have negative 17x squared. I have positive 92x minus 150 equals 0. Any questions on that? It's hard, isn't it, Kaylee? It is. This is a really hard one. There's no doubt about it. Yeah. So if you're feeling a little overwhelmed with this problem, they're not all like this. But I wanted you to see one done all out so that you would know how to anticipate. Hang on. So that you would know how to process through it if you do see one. All right, so this assignment is now completed, so we'll be working through that, getting that ready for homework to be due on Wednesday. Didn't mean that, Thursday. Also on Thursday, we'll have a quiz over 3-1, 3-2, 3-3.